Welcome to a new episode of Your Friendly Physicist and Other Nerds. I am Lucas, the host of this podcast, and I'm in conversation with scientists all around the world that help to create the world we live in today and tomorrow. Together we take a close look at trends and cutting-edge technology, explain how the smallest things influence the big, and generally talk nerdy stuff. So stay tuned, no matter if you're a newbie to physics and interested to learn about the world of friendly scientists, or if you're up for a PhD-worthy nerd talk. Today's episode, I want to start with a short sound clip.
7, 6, 5, 4, 3, 2, 1, 0.
What you just heard was the launch of a rocket, but it's a very special kind of rocket. The rocket is called MAFOIS and it is packed full with scientific equipment that is shot into space to do science. MAFOIS is a German name and stands for Materialphysikalische Experimente unter Schwerelosigkeit, which can be translated to Material Physics Experiments in Zero Gravity. Today is the 28th of February, and just yesterday the MAFOIS 14 rocket launched with in total 14 experiments from the north of Sweden in Kiruna. So I thought it might be a very good time to dedicate this podcast episode to the general topic experiments in zero gravity. Why are we doing such experiments? How do we establish zero gravity conditions? And what is the benefit from all this effort? In this episode, I will answer all these questions. And now, fasten your seatbelts, get comfy, and enjoy the ride. There are several possibilities to create zero gravity conditions, or let's better call it microgravity conditions, because at least on Earth you never can get rid of gravity completely. But all of these possibilities have one thing in common, and that is that you have to throw something down from somewhere. For example, if you jump from a table, you're weightless. Only that it is for a very short time, but still, you're weightless. So if you now increase the time of the free fall, then you increase also the time of being weightless. In Bremen, here in Germany, there is a scientific free fall tower. There you can load your experiment into a capsule, and then you throw this capsule down a tube within this tower, which is 120 meters tall. And overall, this gives you 4.6 seconds of microgravity conditions where you can do your experiments. Of course, everything is under controlled conditions. Now the tube where the capsule falls down is evacuated, and on the bottom there is a bath full of little styrofoam balls that catch the capsule when it reaches the bottom so it doesn't get destroyed and you can recover your experiments. And for some experiments, these 4.6 seconds of microgravity might already be enough. So in Bremen, in this tower, research groups studied, for example, fundamental material characteristics. They investigated the flow dynamics of liquids, which are planned to be used for rocket launchers or gas turbines. And others explore, for example, how oxygen and carbon dioxide can be generated and recycled, respectively, in microgravity. And very exciting, in my opinion, one research group studied the interface between quantum theory, which is the theory of matter, and general relativity, which is the theory of gravity. And these two theories form the main pillars of modern fundamental physics, but they are not really compatible with each other. And if you are interested in these concepts, so quantum theory, general relativity, special relativity, then I recommend episode 3 and episode, I think it was 7, with Gian Inkov, who was a guest here in this podcast, and he's an expert on these concepts. And besides being an expert, he is also a great science communicator and can really well explain all these complex theories and how they connect, and especially how they not connect with each other. So if you're interested in this, give it a listen. And now back to science in microgravity. So from the example we just heard, we also get an answer to the question why we are actually doing this. And the answer is twofold. So some scientists want to have a microgravity environment to study how, for example, liquids flow, how heat is transferred, or how cells grow. So they want to have the influence, or they want to investigate the influence of gravity on these processes. And other scientists, for example, we want to get rid of gravity. Gravity is a relatively weak force, but sometimes it is strong enough for other effects to hide behind gravity. So gravity induces certain flows or convections in materials, and by setting gravity basically to zero, we can analyze materials and measure their properties, for example, the viscosity, density, surface tension of metal melts in very great detail, very precisely. And this is important to understand these materials on a fundamental level and to tune, for example, metal alloy systems in order to have certain desired properties also in regular conditions with then regular gravity, of course. And of course, there are some experiments that need longer microgravity times than these 4.6 seconds you get in this falling tower in Bremen. And for these experiments, you can, for example, do a parabolic flight. And together with my colleagues from the German Aerospace Center, I did a parabolic flight in September 2022 in Bordeaux, in France. And that was really a once-in-a-lifetime experience. And if you ever have the chance to join a team on a parabolic flight, just do it. So, what is a parabolic flight? Imagine you hold a ball in one hand and you throw it in the air, and you catch it with your other hand. And with this, you've just replicated a parabolic flight, where the ball begins its ballistic phase as it falls back to the ground. And with a parabolic flight, it's basically the same, only that you have an airplane with two engines instead of the ball and your two hands. So you are in this airplane, and the airplane flies these parabola, and every parabola follows the same protocol. From a steady flight, the pilots raise the nose of the airplane to 45, 50 degrees, and everything inside the airplane then experiences a hypergravity phase of 1.8 g. And after that comes the injection, meaning the pilots set the engines to idle and weightlessness begins. So first you have overall 11 seconds of free fall upwards, even though there is no up and down in microgravity. But if you would look at the airplane from outside, it would be a free fall upwards. And then the airplane reaches the highest point of the parabola and falling towards the Earth with a maximal degree of, once again, 40-45 degrees. And there you have a free fall downward, so another 11 seconds of microgravity. And after this phase, the pilots pull back the airplane, you have once again hypergravity, and then you are back in steady flight. On this parabolic flight, my colleagues and I, we investigated the viscosity of a liquid copper silicon metal alloy. And as already mentioned, without gravity, you get extremely precise data about their thermophysical properties, for example, the viscosity. And of course, this can be used for material characterization or benchmark experiments, whatever. But you could also use it as an input parameter for example, simulation techniques. And these simulations can then be used to simulate things or simulate certain parameters of your system that are not accessible by experiments. And the more precise your experimental input into the simulation is, the more physically meaningful are the simulation results. So besides the material characterization of this copper silicon system, this was basically the main motivation for this experiment on this parabolic flight. And besides our experiment, there were also other, I think in total there were 10 or 11 experiments on board of this airplane. And they investigated, for example, how to fuel spaceships in zero gravity, or how certain muscles work when a force like gravity is absent. And the entire flight day was one of the best days ever as a scientist. So first you have breakfast with your colleagues where you wonder what to eat when you're floating in microgravity just a few hours later. Apparently porridge and green tea is a good choice here. Then you drive from the hotel to the airport to this company, Noves Pass, which owns and maintains the airplane. It's an Airbus A310. And then Noves Pass is also the overall host of this parabolic flight. Then you register at the counter, and then you enter the aircraft from the back. And the inside of this airplane doesn't look like an aircraft at all. It rather looks like a lab. So all experiments are set up in, let's say, the front 3/4 of this airplane, while the back rather is a regular airplane which holds seats. They are used then for takeoff and landing. But in the scientific area, there you have all your experiments which are fixed to the airplane floor. And you have how the scientists are buzzing around and preparing last things for the experiments and double checking, triple checking everything. And you immediately sense the spirit of this place. You sense that there is something really, really cool happening soon. And this is really great. And then you have the walls and the ceilings and the floor, which are all covered with white paddings and guides that are meant to keep everyone safe during the flight. So we went one final time through our checklist, and then we once again exited the aircraft and head to the Noves Pass briefing room. There we quickly went through the flight plan and slightly adjust the sample order or last details, and then it was time to get dressed for the flight. So we put on our super stylish blue flight overalls. We also got a parabolic flight campaign patch. And as a last step, everyone got some medication against flying sickness. And then we were ready to board the aircraft. We took our seat in the seating area and then take off. And as soon as then the seating signs went off, all the scientists rushed to their instruments, experiments, and set everything up. And then it took another, let's say, 20 minutes or so until the first parabola happened. And there I was standing behind our setup. I waited for the countdown from the cockpit, and then the pilots pulled up the aircraft. I mean, it sounds obvious, but everything started to feel heavier. You heard the numbers. It's only 1.8 times the gravity, the regular gravity. And in some roller coasters, you experience 4 or even 5G. But this is only for a fraction of a second or maybe a second. And in this airplane, in this parabolic flight, there are solid 26 seconds of 1.8 G hypergravity. And this is really heavy. And then I still remember when Dirk, my colleague, turned around, he smiled at me and he said, "Okay, have fun. Nothing is like the first parabola." And he was absolutely right about this. The pilots announce ejection from the cockpit, and then you are weightless. And I started to lift off from the ground, and I fell forward, and my brain expected me to land safely on the ground, just like I have landed on the ground the last 30 years. But this time it was different. This time I just kept on floating, and my brain in this moment could not handle this. There is literally no top and bottom anymore. And this was really a very, very weird moment where I really felt insecure and really didn't know how to react or what to do at all. And after a couple of seconds, it kind of became normal. It's really incredible how fast the human brain can adapt to such extraordinary environments. And then we were floating around in zero gravity, helping with experiments, observing the experiments. And then there was already the countdown for the pull-out phase. And after these 22 seconds of zero gravity, you once again have a hypergravity period of around 20 seconds, and then you are in a steady flight again. And this was one parabola, and overall we had 31 of these. And the entire flight roughly took 3 hours. And then the last parabola is done. You shut down your experiment, and then you go to the seating area and you wait for the landing. And then you're back on the ground, you exit the aircraft, there's a short group picture, and then there is a debriefing in the control room. And then you can prepare for the next flight day. So overall we had 3 of these flight days. I flew only on 1 of these days, and after that you go back to the hotel to relax a bit and to sleep and dreaming of microgravity experiments and parabolic flights. So this parabolic flight gives you 22 seconds of microgravity per parabola, and overall there are 31 parabola, meaning in total you have around 15 minutes of microgravity. And still there are some experiments that need longer microgravity times. So there is another possibility, which is to mount your experiment on a rocket, just like the Malfoy's rocket we heard in the beginning of this episode. And this rocket reaches a height, an altitude of 250, 270 kilometers on average. So it really is in space, where you also don't have any impact of the atmosphere anymore. This stops around 90 kilometers. And there it turns and falls back down to the ground. At some point a parachute opens and the parachute guides then the rocket safely to the ground. There was only one time the parachute failed and the rocket crashed onto the ground, but still it counted as a success since the data could be recovered. But everything else for the next rocket mission you had to build from scratch. And the rocket itself typically is an old military rocket, only that the military parts are replaced with peaceful science, and I think this is kind of beautiful. And the Malfoy's 14 rocket, which launched just yesterday, they had experiments on board from the fields of material science, life science, or biomedicine. So they investigated, for example, how aluminum-based alloys solidified in microgravity. They investigated the behavior of gold nanoparticles, or how brain cells recover under microgravity conditions. And if you're interested in how such a rocket flight works and you want to hear a little bit more details, you can listen to episodes 4 with Melanie Klosel from the German Aerospace Center, or episode 5 with Lennart Reb from Technical University of Munich. So Melanie had a 3D printer on board of the rocket and investigated how to 3D print a metal powder in microgravity, and Lennart shot some solar cells into space and studied their efficiency and degradation mechanism in space. And then there is a fourth possibility, which is the International Space Station, the ISS. The ISS flies at an altitude of around 400 kilometers, and at this height you still feel the Earth's gravity. So you might wonder, why are all the astronauts you see in the news or on these YouTube videos floating around there? And this is because also the ISS is falling down. So the ISS is orbiting around the Earth with a certain speed, so that it constantly falls down beyond the horizon. So it never stops falling down. It's basically a never-ending free fall. And this gives you continuous microgravity also on the ISS. And there are labs up there. Most of the experiments are remotely controlled from the Earth and happening at night when the astronauts sleep, so they don't disturb the experiments. The experiments are super sensitive to vibrations and other disturbances. And in this way, the ISS allows, for example, for experiments in the fields of solidification of metals and alloys, crystal growth in semiconducting materials, once again thermophysical properties, or diffusion experiments, glass forming materials, or the investigation of polymers or ceramics at some phase transition, etc., where you really want to study these materials in such great details that you want to get rid of gravity. And this you could do also at the ISS, which is also kind of cool. So in summary, one can say that, it is a tremendous effort to do science in space and in microgravity, but still the knowledge, the experience, the understanding you get out of these experiments, they contribute so massively to also solve problems down here on Earth. And a lot of common technology that is applied already today and we are using every day comes initially from the space science sector. And there is another argument I heard a lot in recent times. of course, space science, space exploration, rocket science, everything that has to do with space or with rockets and so on, it is prestigious. And space agencies, they kind of want to show off with their projects. Yeah? And with this show off, they of course want to attract intelligent, curious, motivated young people to work with them and develop with them together a new project that will eventually contribute to solve the big challenges of our time. So this is also a second reason, I would say, why we are doing science in space. I hope you learned something today about experiments and science in microgravity. If you have questions, feedback, wishes, or anything else, let me know in the comment section on Spotify, or you can always reach out to me on LinkedIn or Instagram. Also on Instagram you find some pictures and videos about the Matthäus rocket and also the parabolic flight. So then you also have visuals in combination with this podcast episode. And if you like this episode, I would be very happy if you share it with a friend or a colleague. And if you have an exciting story you want to tell, for example in this podcast, feel free to drop me a short message anytime. Thanks for tuning in, take care, and see you soon on the next episode.